The paper is Reimagining Secret Sharing. My co-authors are Mihir Bellari and Wei Dai, and I'm Phil Rogaway. The classical secret sharing problem was independently proposed and solved by Bob Blakely and Adi Shamir way back in 1979. The problem imagines a dealer in possession of some secret message M it wants to distribute. It breaks the message into some number of shares and gives one to each shareholder. At some later point in time, shareholders can pool their shares and try to recover the original message. Recovery should succeed if an authorized set of shareholders contribute their pieces. Note that on recovery, shares are either correct or missing, with missing shares being marked and no share ever being wrong. The classical solution to this problem, due to Shamir, works for threshold access structures, meaning that the recovery succeeds when there is at least some particular number of provided shares. Shamir's solution involves polynomial invaluation and interpolation over a finite field. It's not hard to formally define what a classical secret sharing scheme is. In terms of syntax, we would say that such a scheme consists of a pair of algorithms, one to share out messages and one to recover messages from shares. The former takes in a message and probabilistically outputs an n vector of shares, where n is the number of shareholders for the scheme. When we say that the sharing algorithm is probabilistic, we mean that its behavior depends on internal coin flips, so that different n vectors of shares will likely result from sharing out the same message twice. The recovery algorithm takes in an n vector of shares, or alternatively, a share can be marked as missing, which is what this symbol represents. From this n vector, it outputs a message. Associated to our pair of algorithms is an access structure, A. The access structure specifies which sets of shareholders are authorized to recover the message from shares. Formally, an access structure is just a set of subsets of the numbers 1 to n. It has to be monotone, which means that if some set of users are authorized, it's in A, then so too is any superset of it. There's only one security property for a classical secret sharing scheme, and it's this privacy property. It says that if some set of users are not authorized, then what they see when you share out some first message looks just like that which they would see if you had shared out some alternative message. Classical secret sharing is a simple and elegant problem that's now over 40 years old. There has been a tremendous amount of work on the problem during this time. In view of this, it would be reasonable to expect that there shouldn't be any basic concerns about secret sharing that wouldn't have been addressed long ago. But I'm going to claim the exact opposite, that there exist basic gaps between what a human user would likely want or expect in a secret sharing scheme and what classical secret sharing and schemes like Shamir's actually provide. To start to illustrate this gap, let's imagine a simple scenario in which a journalist D, for dealer, has an archive of highly sensitive information encrypted with a strong passphrase. Think the Snowden documents or the Panama Papers. To help protect the materials, and herself, the journalist D wants to hand off the encrypted file and share out her passphrase to colleagues A, B, and C. Any two should be able to reconstruct. D will be meeting her colleagues on different days as she travels internationally. It is crucial that, as she travels, crossing international borders, the passphrase never resides anywhere but inside her head. But that's already a big problem. If the shares A, B, and C are generated on Monday, when A is needed, what to do with B and C? It's impractical to memorize them, but D can't just write them down or store them on her laptop or phone, as that's equivalent to storing the passphrase in the clear. Nor can D recreate B and C at the time that they're needed, because, recall, the sharing algorithm was probabilistic and needed to be for security. D could retain the coins used to share the passphrase, but that doesn't work either. With Shamir's scheme, say, possession of those coins, along with any one share, already implicates the secret. We see this simple use case as motivating a need for reproducible secret sharing, that it should be at least possible to regenerate shares from a strong passphrase, retaining strong security. Let's continue our story. Shortly after Dee reaches her destination, she mysteriously vanishes. At the same time, a certain intelligence agency has secretly infiltrated C's computer and replaced her share with another. When parties A and C converge to reconstruct the secret, they're surprised that it doesn't look all that interesting. While they don't know it, the reason is because it's not the original message. Recall that the classical secret sharing definition only describes what happens when some shares vanish, but enough good ones remain. The definition says absolutely nothing about what happens if even one share is changed. There's no reason to think that the adversary can't force the recovery of any secret it wants by just changing a single share. Indeed, Shamir's secret sharing has pretty much exactly that property, that a single share changed can result in the recovery of any desired message in the message space. Of course, we would prefer that in a scenario like this, recovery should generate an error message and not a bogus secret. Let's imagine a different continuation of our story. Now all three shareholders come together to recover the secret. Party C's share remains corrupted. When they get together, perhaps this time they somehow learn that there's a problem. Maybe the archive they recover looks like a bunch of random bits. But the parties don't know what the problem is. Maybe the dealer D messed up, or maybe the software has bugs. If they had the insight to guess that C's share was corrupted, and they tried to recover without it, they would actually get the correct underlying message. But the shareholders have no way to know this. We would like a scheme that is guaranteed to recover the original message in a case like this. In fact, it should tell us more, explicitly suggesting that the first two shares implicate M, while the last share has been messed up. There is a secret sharing variant called robust secret sharing that will indeed guarantee recovery of M. But there turns out to be a problem with that notion. For example, it's inappropriate in settings like 2 out of 4 secret sharing, which we view as a completely normal and legitimate case. Our road to reformulating secret sharing begins by adopting richer syntax than what classical secret sharing used. Let's focus first on the sharing algorithm. It still takes in a message and still outputs a vector of shares. But there's now this new input for the coins. The algorithm is deterministic, but for these coins, the user is free to provide uniform random bits, which will give a privacy notion, just like the classical one. To get reproducibility, however, there are other possible options for use, like making the coins random bits associated to an installation, or even making the coins a constant. We're going to demand best possible privacy for whatever coins have been provided. Then there's this tag, which we also call the associated data. It's information that we don't want to split up, but do want to bind to a sharing. It could specify, for example, that the date and location at which a sharing occurred. Or it could specify the dealer's intent about recovery, like, only recover if I'm dead. The first argument, the access structure's description, seems like a natural thing to provide to the sharing algorithm, but recall that in the prior formulation, it wasn't provided, but was treated as something fixed, which is much more limited. Moving on, the recovery algorithm no longer takes in a vector of shares, but instead a set of shares. This better matches the human context, where a bunch of people come together to recover something, and we don't come numbered like I'm party 2, so there's nowhere in particular to slot our share. We're a set of people, and the underlying syntax needs to reflect that. The output of recover includes not only the recovered message, but which shares are deemed valid. A shareholder deserves to know if the recovery algorithm used his contribution. For somewhat technical reasons, we also demand that the recover algorithm recover the random coins which were used by share. but there's a good chance that the recovering party doesn't actually care about this value. It is important that when you apply the recover algorithm, there's at least the possibility that the algorithm says no, that it's unable to recover anything. Because it's better to have that happen than to return garbage. Finally, there's this input to recover, which is used to specify a priori information that the recovering party might know. It might specify that a particular access structure needs to be used, or that some particular share or set of shares are known to be valid. For example, they might have been signed by the dealer. That's already a great deal of syntax, but it's important because the syntax profoundly impacts what you can define, what you even have language to talk about. On top of our syntax, we define three basic security goals. The first, privacy, says that unauthorized sets of shares should reveal the least information possible given the combined entropy of the secret and the provided coins. We formulate this to be a strengthening of the classical privacy goal, where the coins were assumed uniformly random. Achieving our strong form of privacy not only enables reproducibility, but also other goals, like hedging, which says that schemes should work as best as one can hope for in the case of catastrophic randomness failures. The second goal is an authenticity property. It says that a share held by a shareholder will recover, if anything, only the one secret that was committed to at the time of the sharing. This will hold no matter what other parties try to do to get you to recover the wrong thing. Finally, there's an error correction property. It says that if there's only one plausible explanation as to which shares implicate what secret, then recover is obliged to identify that secret and those shares. If this isn't the case, that there is not an unambiguous secret underlying the shares, then recover needs to say that. You'll notice that the three properties correspond to the three scenarios I gave, although each property can be motivated in multiple additional ways. The syntax and security properties I've sketched didn't arise in a vacuum. Rather, we contemplated usage scenarios like those I discussed at the beginning of today's talk, and we interacted with implementers, journalists, and a whistleblower about what they wanted in a secret sharing scheme. We reversed engineered a couple of artifacts. In particular, we looked at Sunder, the user-facing tool from the Freedom of the Press Foundation, and we looked at Rusty Secrets, the cryptographic library that Sunder was based on. Finally, we reasoned by analogy, because secret sharing is really very much like symmetric encryption, as I'll now show. In the classical setting for symmetric encryption, you would take your message M, flip a bunch of coins to encrypt it, and later you could decrypt the ciphertext and recover the plaintext. And that's pretty much the same thing as happens in the classical secret sharing setting. The share and recover algorithms are like classical encryption and decryption algorithms. The dealer and reconstructing parties are analogous to the sender and receiver, and the ciphertext is like the vector of shares. So many of the things we've learned about how to make symmetric encryption stronger and more useful ought to apply to secret sharing. In particular, we can mirror the changes that turned classical probabilistic symmetric encryption into authenticated encryption. What are those changes? Well, first, the possible return values for decryption needed to be expanded to include an indication of invalidity. So too in secret sharing, we need to be able to say no, that these shares are just too messed up. Second, internal coin flips were removed from the encryption algorithm, and those coins were replaced by a nonce input. So in secret sharing, we do the same thing, surfacing any randomness used by share so that we can lower definitional requirements on it. Third, in authenticated encryption, there's an entirely new argument, the associated data, or AD, which is authenticated but not encrypted. So too for secret sharing, we add in a new argument, the tag, that functions like the AD. Finally, there's this argument A, the access structure, that we provide to the sharing algorithm to configure what we want it to do. While this isn't something in the formulation of AE, actual implementations of AE often do have something like this, to configure the mode. While we can't explain all of the changes we've made to secret sharing via this analogy, it gets us pretty far along the way. One way to formalize classical privacy is to equip an adversary with an oracle that takes in a pair of messages and always shares out the left-hand query or alternatively the right-hand one. Then as long as the adversary only gets to see unauthorized sets of shares from each sharing, it shouldn't be able to tell which of the two types of oracles it has. This is sometimes called a left or right style definition. We'd like to generalize this by saying that the same property continues to hold even if the adversary knows and chooses the coin's R. But that's asking a little too much, because an adversary who fully knows the left and right queries and the coin tosses necessarily will be able to tell from an unauthorized set of shares which messages got shared out. So we formalize that if the message and the coins together are unpredictable, then the adversary can't do well with the left or right game I've described. In brief, we demand the maximal privacy possible given the joint distribution on messages and coins. Authenticity is a little simpler to formalize. Giving the adversary just about every benefit one can imagine, we will let it choose two sets of shares that have at least one share S in common. If you would recover one secret, M, from the first set of shares, and a different secret, M prime, from the second set of shares, then we'll say that the adversary has defeated authenticity. So for a scheme that achieves authenticity, from the point of view of a shareholder who comes to possess some share S, he can be sure that there's only one thing that could ever be recovered making use of his share. Informally, error correction can be understood as an exercise in explanation seeking. If one can explain the set of shares that is provided to recover in some one unique way, that a particular subset of shares are valid and implicate M, while the rest are invalid, then you are obligated to find and provide that unique explanation. If there is no such unique explanation, then we demand that recover say that, returning an indication of invalidity. The intuition above can be formalized in a couple of different ways, either based on looking at the scheme's sharing algorithm or looking at its recovery algorithm. The two approaches turn out to be equivalent. This slide shows the recovery-based approach. Our definition implies robustness in cases where robustness is possible. To achieve our privacy and authenticity properties, we provide a generic transformation, AX. You start with a classical secret sharing scheme, like Shamir's, and embellish it using a pseudorandom generator and a hash function. Basically, you encrypt the message M you want to share out using the pseudorandom generator and include the resulting ciphertext C in each share. The key used for the encryption is obtained by hashing the message, coins, access structure description, and the tag. Then you share out the encryption key using the lower-level scheme, like Shamir's. The random coins for this sharing are again obtained by the hash of the message, coins, access structure, and tag. There are a few more details, but in the end, it's a simple and efficient recipe. There's only a tiny amount of overhead beyond the one hash in the PRG application, as the lower-level secret sharing scheme is only used on messages of a fixed size, like 16 or 32 bytes. There is some more work to add in error correction. We structure this additional work so that the sharing algorithm is unchanged and the recovery time is not increased for the usual case where all the presented shares are valid. In the end, one starts with any classical secret sharing scheme and puts around it this wrapper obtained by composing our two transformations, thereby obtaining a practical scheme that achieves far stronger security properties than the original scheme did. It is this twice transformed scheme that we suggest be implemented in libraries and user-facing tools. I'll wrap up by acknowledging that ours is an unusual paper for pets. There are no user studies, implementations, or attacks. What there is a reconceptualization of a basic notion that we believe to have direct value in creating privacy-enhancing technologies. Can you actually enhance a user's privacy by hacking cryptographic definitions and building schemes that conform to them? We believe that if you hack the definitions in the right way and build good schemes meeting them, This is totally possible. Just as authenticated encryption transformed symmetric encryption into a more applicable and easily used tool, we hope that we have done the same for secret sharing.